Good afternoon, everyone. Today we're going to continue our discussion of multiple linear regression using the LM function of R and also the matrix multiplication, okay, which is really the foundation of how the LM function works. So let's have a quick review that the multiple linear regression equation is based on this matrix equation, the y is equal to your dependent variable is equal to x times beta. X is your matrix of your predictors, including the column for the intercept, this one here. Beta is your matrix array for your predictors, including the intercept. And then plus your epsilon. Why do we add this? Because this is your, let's assume this is your actual value. This is your predicted value class. The XB is your predicted value. Then chances are there will be differences between your actual value and your predicted values. And so in order to make the equality true, then we add the residuals array. If we remove epsilon here, class, then the y here becomes a y hat. Y hat is your predicted value, which is equal to x beta. And we said that your y is comprised of an n by 1. It's an n by 1 matrix. You have your n observations by one column, rows of observation, n. Then your x is your array or matrix consisting of p predictors and n observations. We add we add 1 to accommodate the intercept. We can represent this by p, n by p, and just assume that p includes your intercept class. And your beta also, p plus 1 to include the intercept. We can also define this as p by 1 with the understanding that p is includes the beta null, the intercept. Okay, so y is equal to x times beta, matrix multiplication. And we learned last time that how is that done, class? How do we solve the beta matrix? Okay, this y is your the values of your actual values minus xb. This is your predicted value. So the difference between this is your epsilon. This is your residual. But in OLS, we would like okay, what we want is to minimize the square of the residuals. So what we can do is we multiply this by y minus xb and y minus xb. However, since we're dealing with matrices, and y minus xb times y minus xb will not work because of the nonconformity of the dimension. So we have to get the transpose of the first matrix so that these are multiplicable. By getting the transpose of the first set and multiplying it by this one, then you're actually getting the square of the difference between the actual value and your predicted value. Okay, so this is actually the square class. This times this, okay, will only be possible if the first one is transposed. So this will now give you actually your epsilon squared. Okay, so this can be reduced into this one. And then the final class, the final is that when we use differential calculus, okay, by difference, by getting the derivatives, partial derivative of your beta, okay, your function, the sum of your squares, SB, getting the derivative with respect to your beta, you get this final equation. Final equation is your beta hat is equal to x transpose x, sorry, inverse x transpose y. Okay, so that in a nutshell, class, is your is how you compute for your predictors. Again, this equation was born out of the fact that we are minimizing the errors. How do we minimize the errors? By getting the by differencing, getting the differentiation of your squared errors function, get the difference with respect to, differentiate with respect to the beta. Okay, so you get this equation, which when you solve beta for, will give you this one. All right, so that's where the equation of x transpose x inverse x transpose y comes from. Okay, so we are certain that this one will produce the least residuals squared. Okay, and this just tells us how to, I just explained here how the simplification was done. And then finally this one. So I'm just showing you how the computation was done. All right. So what we did last time was we made use of the wage data set. Make sure that your wage data set is already loaded. Okay, we did this already before, so we're not going to redo this. Okay, and what we did was to create, this is our wage data set. There are many predictors here. You can see that there are factors here. So what we did was to choose these predictors consisting of both numerical and factors. Education, experience, tenure, number of dependents. These are your numeric predictors. And you have three factors: non-white, female, and married. When I say factors, these are predictors that are categorical in nature, and that's they use for classification. When we use non-white, let's take a look at this one, class, non-white. Where is non-white here? Non-white. Non-white is where? Here. So this data was arranged in such a way that 0 will be your white, okay, white class. That will be your benchmark or your reference. The non-whites here will be your 1. So anyone here is non-white. Okay, so I think that's the best way to convert your factor, your categorical variable, into a factor. Okay, and we named the those that get the non-benchmark as 1. Those that are zeros here are the whites. So this one, for example, the first observation, this is white. White, 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 etc. Then you have your first non-white is this one. Non-white, non-white. So can you do the reverse? Yes, of course. If you want the non-white to be the benchmark, then we let this one, the zeros will have to become 1, okay? And the ones here will represent your white. So we can name it, we can rename this as white, okay? And all the zeros here will become 1 since they refer to white. And then all the 1 here, 1 will become 0, okay? And then they will become the benchmark or the reference reference level. Okay, this is just nomenclature, how to name your predictors so that there's no confusion. Here, if you take a look at this, female, okay, this is female. All the ones here are female. Therefore, all the zeros here are your benchmarks or reference levels. They are your males. Okay? And lastly, we have here married. So you know that in the data, married and single. So all the ones here are married. The zeros here are your single. Okay? So can we interchange it? Yes. You can make, the results will be the same, only the sign will differ. If married is positive, then if we make single as the as the benchmark or as the non-benchmark. Okay, so this becomes single, and all the zeros here will become 1. Then the value of the coefficient will be opposite, the opposite sign. Okay? All right, so that's what we did last time. So we run this class. If you haven't run it, please run it now. Okay, so let me just run it. Okay, chosen predictors. So we have this education, experience, tenure. And then I'd like to, okay, overwrite these chosen predictors by intersecting it with the chosen predictors and the names of wage 1. So what will this do? It will write off, it will overwrite chosen predicts spreads, and then it will get what's common, intersect. What's common with chosen spreads, which is this one, and wage 1, which is our object here. So it will look for what's common between chosen spreads and wage 1. We just wanted to make sure that these variables that we chose are really part of wage 1. Okay, so let me run this. There you go. So what I can find in chosen spreads, I can also find in wage 1 because they're all the same. They're all complete. All right. So next, what we did was to create this object formula for our cross-sectional data. As that formula, we paste this text, wage tilde, this is tilde. This symbol we use for regression, and paste the chosen spreads, then collapse. Collapse it with equal to plus, which means that the chosen spreads are here. Edu, experience. If we did not put collapse, then it will just type all this text with no plus sign, but we need the plus sign class. So if we run this whole function, this whole code chunk, then here we go. What is this type class? It's a formula. Okay, it's a formula class. And then where will our formula go? If you take a look at the formula here, it will fall under data. Sorry, it will fall under values class here. So it's just like a vector class, this one. And then we printed it using formula wage associated with education, experience, tenure. This is our regression equation. Okay, so inulat lang dito. All right, then remember, we'd like to make use of wage as our, here is wage class, the first column. We'd like to create a model where we would like to relate or associate or let's see, predict, can be, our wage variable using these predictors. Education, experience, tenure, non-white, female, married, number of dependents. All of these 7 predictors. So how do we do that, class? Again, the very powerful matrix model matrix equation beta hat, predicted value is equal to x transpose x inverse x transpose y. So we said that we can do this in R. First, let us create your X matrix and your Y matrix. Your X matrix has several, okay, this is, remember, this is how your X matrix looks like. This one, class, diba? Okay, this one. We need to create this. The first column are ones, and the rest are education, experience, tenure, etc. So we need to create that matrix. And we said that we can make use of the model dot matrix function. Here you go. Here, class. Model dot matrix. And we use the function formula CS. What's formula? Formula cross-section, class, is this one. This one, right? So R will know that the X here are this one, education, experience, tenure. Okay. It recognizes that this one is your dependent variable wage. and this one are your independent. So model that matrix, okay, it will give us the X matrix. Data is equal to wage. So when you run this class, okay, kindly run this, you will have the X, this XCS class. Let's print this. Okay, there you go. Diba? You have your intercept, all the ones here. Okay, and how many total columns do we have? Eight total columns class. So it includes all your 7 predictors: education, experience, tenure, number of dependents, non-white, female, married, plus your intercept. So this is your X matrix. Okay, and then your Y, since it's only one column, then you can just use as that matrix. Okay, and it's the wage column from your wage one. So if you run this class and print it YCS, you'll have this. You'll have this matrix. Okay. How many rows? 526. N, because our wage one data set has N 526 observations and only one column, your dependent variable. So that takes care of your Y. Okay, if you check the class of CS or YS, and then it's a matrix or array. And then last time also we we determined N, which is the number of rows of CS, and printed it. We know that there are 526 observations. And for P1, the number of predictors, we get the N columns of XCS. Okay, print P1. So there are 8 columns, including the intercept, the first column, and then your 7 predictors. And we can print this, our design matrix dimensions. Design matrix dimensions, N is equal to 526. Then quotations, comma, regressors, including intercept, is equal to, then leave out P1 for it to print. Okay. In your case study, you can make use of this class. Okay. But make sure not to print it by putting here echo is equal to false. It depends on how you do it, but it will still print this one. Okay. All right. Remember again, this is what we want to do. So how do we class compute for this one? The first item here, X transpose times X. Okay. And this one, X transpose times Y. These are actually cross products. And in our okay. So there are 2 ways to do this. First is by the long cut, X transpose. This is X. How do you get the X transpose class? The transpose of XCS. Okay. And then percentage times percentage means you multiply it with this one. Okay. So this one class. So quick question class, how do you get the inverse in R class? So we have to get the inverse. Kindly take a look class, Google, give me the function. How do you get the inverse class? In R. Because we need to get this. How, class? Kindly check, please. What's the answer? Waiting for your response, class. If you Google that, class, what's the function to get the inverse of a matrix? Of a matrix multiplication in R. This one. Because we have here X transpose times X. This is the X transpose. And then times X. Multiplication is percentage times percentage. Okay. Percentage times X. So this one class is X transpose times X, but without the inverse. So there's an answer here. How do you get the inverse? Okay, is it in class? Kindly check. Second opinion class, by getting the are we able to get the inverse of a matrix multiplication? Is that the function class? Hello, class. Waiting for your response, class. Come on, everyone. If it's in, you have to install a package called mat library. Is that the only function, class? Sean, how about the others? So Sean already answered, Charisse answered. How about the others, class? Is there another way to get the inverse of a matrix multiplication? Yes, okay. So that's solve, class. Solve. Solve will get the inverse, class. Okay. So if I put here solve, just by taking a look at this function, class. Okay, take a look at this, class. So this one, class, this is the transpose of our matrix X multiplied by matrix X. So this is the one. And then solve it, class, to get this one. And then again, multiply it, matrix multiplication, by the transpose of X, which is this one, and then matrix multiply again with Y. So technically, this is the whole function of that. Okay, but there's a shortcut for that, and there's a better way instead of using this, class. Instead of using this complete function, there's a better way for us to do that. And we learned that last time. Number one, we said cross product. Cross product, class, you can get the multiplication of a matrix with its transpose. Okay, this one. Cross product XCS. Now why only XCS? Because this means that you are multiplying it with XCS. There have to be two components there, XCS and XCS. If I don't put XCS here, let's like this, class, then what I meant was, this is what I meant really, XCS and XCS. That's the cross product. But you can just put one, and our understanding is already to be XCS and XCS. And then we said that X times XCS times XCS cannot be multiplied, class. Okay, unless it's a square matrix. XCS multiplied by XCS cannot be multiplied unless it's a square matrix. What do I mean by that? So let's say this is 3 by 3, and this is also 3 by 3. 3 by 3 is a square matrix because your rows and columns are the same. So can they be multiplied? Yes, because they're conformable. And the resulting size is 3 by 3. Okay. However, if they have this, if they're not square, for example, in our case, what's XCS? XCS is n, number of rows is n by p. Let's say p already includes the intercept. Okay, let's just name it as p, n by p. So this is also n by p. Are they conformable? No. This is the column of the first matrix. Compare it with the row of the second matrix. Hindi pwede. They're different. So that's why you have to get the transpose of the first matrix in order for this to be multiplicable. So this becomes n by p. Sorry, p by n, class. P by n. You're getting the transpose of this. So the resulting matrix is, this is multiplicable n by n. The resulting matrix is p by p. Okay? All right. But why not? Okay, there's this question. But why not x cross section, x cross section? Why not this get the transpose of this one? Why is it the first matrix? Again, what's the size of this? This is n by p. Okay, and this one will become p by n, right? So multiplicable, yes, class, that's correct. But this becomes n by n. So it's n by n. Okay, and that's not what we want, because what we want is the size of the beta, the parameters, which is p class. So we want the result to be size p. The row will be p and not n. Because if you do it x cross section times x transpose, yes, this can be multiplied. Okay, this can be multiplied, but it will give us the wrong answer because the answer is n by n. And n is not the size of your parameters. The size of your parameters is p. Okay, so that's why you get the transpose first and then multiplied by x. Okay, so that's why this one gives us x transpose times x. And then if you get the cross product class, okay, kindly do that. If you don't have it yet, or if you closed you might have deleted the results here. If you check x transpose x class, I'll not run it anymore. I ran it a while ago. X transpose x class, this one. You notice it's 1 by 8 by 1 by 8. So this is an array class. Okay, it's an array. How do I know it's an array class? It's an array by checking. If I check class of x transpose x. X transpose x, the class of that is, it's a matrix class, matrix or array. Okay, so if you check class this one, x transpose x, let's have this printed here. All right, take a look. Okay, intercept, education. Okay, these are your parameters. These are your parameters, including the intercept. So this is p by p, this is 8 by 8. And later on, when we multiply it to the x transpose times y, it will now become a p by 1. Okay, so one row only with all the p's, with all your betas. That's what we need, class. That's what we want. All right, so for this one, class, for this one, we are multiplying x transpose times y. We all, again, use the cross product. Cross product x cs, then y cs. It will also get the transpose of this. Okay. All right, so this becomes this one, class. X transpose times y. Cross product of xcs and ycs. Okay, and then from this class, we can now get the beta. Beta matrix class is, we now use the solve class. This will now get the inverse of xtx. The x transpose x here, class. To get the inverse, we use the solve function. So solve the inverse of this multiplied by x transpose y, which is this one. Okay, so this becomes, class, this now becomes your p by 1 matrix, which consists of your predictors. So please run that. And if you run that, class, let's print beta. So this is your beta math. So it's now a p by 1 matrix. The p there includes the intercept. Okay, I'll wait for you, class, to please chat in the chat box, class. By the way, I forgot to mention, Sean, you gave your answer a while ago. This was not seen by your classmates. No? So next time, please, everyone, when you share your answer, please share it to everyone so that everybody can. Pakishare nga, Sean, just to backtrack a bit, what you shared a while ago. When I was asking for the function to use in getting the inverse of matrix or a matrix multiplication of the product of a matrix. Sean, kindly please share that message if it's in po. Hello, Sean. Hello. Okay. Step out si Sean. Okay, I think he stepped out. To class yung answer niya kanina, no? Okay. You can use the in function class, kaso it should come from MATLib, no? Mat library. Otherwise, class, you can use the solve function of R. Okay. So quickly, class, what's the meaning of this? 0.57, class. So how do we interpret this? It means that this one, education, class. This is the marginal effect of education on your wage. Okay, so and what does it mean? For every 1 year. Why did I use 1 year? Because education is in years. For every 1 year increase in education, there's a corresponding 0.57. Okay, hold the line, class. Okay, all right. So what I was saying is that the value here, class, 0.57. And by the way, class, these values are unique, and this is the best. This is what we call the BLUE, blue. BLUE, class. Best linear unbiased estimator. We derived it using, we got the partial derivative of the function of your beta, okay, with respect to the beta, okay, and equated it to 0. Okay, when you do that, class, when you get the differentiation of a function and then equate it to 0, you're getting the minimal or maximal value. In our case, it's the minimum. Okay, and then as we said, it resulted into X transpose X inverse X transpose Y. Sorry, I hope you don't mind me keep on repeating this. Okay, this is the fundamental of our regression equation in multiple linear regression. Okay, so back to the meaning, class, $0.57. I just rounded it off to 0.57. For every 1 year increase in education, why did I use year? Because education is in years. There's a corresponding $0.57 increase in wage, and then ceteris paribus, class, CP. Ceteris paribus means all things being the same. What does all things being equal or all things being the same mean? It means that I'm only increasing year by 1. The others I'm not going to increase. Okay, whatever the value of tenure, number of dependents, non-white, etc., whatever their values are, will remain the same. It's only experience that I'm going to increase by 1. So for example, if experience for a particular respondent was 10, if we increase 10 by 1, make it 11, then the hourly wage of that individual will increase by 0.57. Okay? If the hourly wage, let's say, was 2.00, if I add education by 1, ibig sabihin, the number of years of that individual increased by 1, okay, the hourly wage would have become 2.57. Okay, same thing, class, with experience. A 1 year increase in experience, which is also year, will result into a around 0.022 dollars increase in hourly wage, ceteris paribus. For tenure, 1 year increase in tenure, 1 year increase in the company, working in the company, will on the average increase hourly wage by $0.138 hourly wage, no? Ceteris paribus. Okay, now we go here, class. These are your factors. Your factors are your categorical variables. They are your classifiers. So if you take a look at this, class, I think I mentioned this a while ago. Okay, your wage data set. You notice there's this variable non-white there. Non-white. And there are zeros and ones there. What does that mean, class? Zeros and ones. The ones that are one, class, the ones there, refer to your non-white. Okay, so in the original data, they ask you, are you white or non-white? Then perhaps my option done, you click non-white. Okay. Now that's a categorical variable. We can use that in order to differentiate between how much is the hourly wage of non-whites and white people. So that's a very important factor or categorical variable. Okay. So we said that factors should be converted into dummy variables. Okay. Dummy variables. And that the number of levels, your dummy variables will be your k minus 1. What is your k? K is the number of your levels and minus 1. For our race, class, non-white na to, for our race, we have two levels, non-white and white. So therefore, how many dummy variables are you going to include? K is 2 levels, white and non-white. Minus 1, so therefore only one dummy variable. That's why if you take a look at your wage data set, you only have there non-white, okay, and no other level class. You can only see there non-white, okay. Now, a non-white class, for non-white, okay, the non-white class will be made into a 1, okay, and you have other values there that are 0. So if you see that the values are 0, that means it refers to your reference variable, and your reference variable is the opposite of this one, which is white. Okay, so what we did was to convert your categorical variable, your factor, into a dummy variable. Okay, and you have to choose. You can choose your benchmark or your reference value. In our case, our reference value, class, is what we chose. The reference value is the one that gets 0. So the one that gets 0 is white. And then we rename this variable to be non-white. Okay, so non-white siya, di ba? So pag ganun, class, lahat ng non-white will get a value of 1. Okay, and all the whites will get a value of 0. Okay, so that's what happens, class, no? That's what happens. Okay, so now, what's the meaning of this, class? On the average, okay, when you interpret this, always interpret this with reference to your benchmark variable. On the average, non-white employees get $0.11 less. Less, class, kasi negative to, no? Less than their white race counterparts. Okay, so you always interpret a factor like this with reference to your comparing it with your reference or your benchmark variable. So you have to know, class, what is your benchmark variable. Okay, on the other hand, this one, female. So on the average, female employees receive $1.76 hourly wage than less class than their male counterparts. Okay, so si females, they receive on the average $1.76 less than their male counterparts. For married naman, class, they receive $0.46 in terms of hourly wage more, kasi positive to, more than their single counterparts. Say if the opposite is single, then single class. Okay, and lastly, class, this one. What's the meaning of this class? On the average, employees with 0 years of education, because the intercept class is the value of your dependent variable when all your predictors are equal to 0. So the average, ano to, 1.76 ba ito? Sorry, 1.76. On the average class, employees with 0 years of education, 0 years of experience, 0 years of tenure, 0 dependents, okay, who are white, who are male, and who are single, get an average salary of negative 1.97. Yun ang average salary nila. Who are those? Those who are, okay, single. Bakit single class? Kasi remember, class, married dito is 1. Si single, 0. Diba? Kasi ano to eh, this is your factor. One of them is 1 and 0 if there are 2 levels. No? So, sino yung 0 dito? Si single. Sino yung 0 dito? Si male. Sino yung 0 dito? Si white. Okay? So, on the average, white, male, single employees with 0 years of education, 0 years of experience, 0 years of tenure, 0 number of dependents, get an average hourly wage salary of 1.98. Negative, no? Negative 1.98. Yun ang average salary nila. Of course, class, it has no practical meaning because you cannot have an average salary of negative. Ibig sabihin nun, kayo pang magbabayad sa company for every hour of work na ginagawa. No? So it's only used because the intercept class is used in the model. Okay, but this has no practical meaning or practical implication. All right, so let's move on. Comment, please. Are you able to follow, class? Is the explanation clear? Explanation clear, class? Okay, comment, please. Okay, good. How about the others? Let's give your classmates a few more seconds. I'm getting only 4 responses. How about the others? Okay. All right. I hope you're getting it, class. If you have any questions, please feel free to raise your hands. Okay. So we leave this class, this beta mat, this beta matrix that we created. So the beta matrix that we created, class, was born out of our model, X transpose X, X transpose X inverse X transpose Y. Okay. And let's just change some of the column names here. Okay, so when we get now the beta mat, okay, we just changed the column name of, a while ago, this is V1. We just made it as estimate matrix. Okay. This is the printout class of our beta mat. Okay, so here I just explained how this was done. Okay. All right. Now we go to the prediction matrix class. Checking the time. Okay. Prediction matrix class. What's this? Y hat matrix. Okay. Y hat class. Remember, class, the equation Y is equal to X times your beta plus epsilon. Remember, class, that this one is your predicted value of y hat. Okay, so it's equal to x times beta. So that's your Rx is our XCS, right? And then matrix multiply it by beta mat. Okay, so X CS, this is our matrix, the array, multiplied by, so it's not a scalar multiplication. So it's what we call a matrix multiplication. And in matrix multiplication, the multiplication part is percentage cross asterisk percentage, this one class, multiplied by your beta mat. Okay, check class XCS, what's the size of XCS? And by P, assuming P class includes your intercept. Your beta mat class is P by 1, right? P observations, including the intercept, by 1. That's your beta mat class. Conformable, multiplicable, yes. What's a resulting matrix? N by 1. Is that supposed to be the size of your y hat, of your predicted values? Yes. Your y size is n by 1. Then your y hat should be n by 1 also. Okay, each value will have their own predictions. Okay, so when you run that class, okay, let me pause for a while, and I'll wait for you to tell me if you have if you're able to get this class y hat mat. Kindly please chat in the chat box. Check it, the values class. It should be n by 1. There should be 526 observations and 1 column. Please confirm class if you got that result. 526 rows of observation by 1. It's a prediction class of your it's a predicted value class of your model. Okay, thank you, Lara. How about the others, please? All right. I hope the others are able to follow. Okay. All right. So we now have our y hat matrix class. This is our predicted value matrix. Okay. And then how about the residuals class? The residuals is simply the difference between your actual value minus your predicted value. Okay, so if I show y hat, excuse me, class. Okay, y hat matrix class here. Where's my y hat matrix? Here, class. There you go. Here. That's my y hat matrix. So let me just copy the first one. Control C, Control V. So this was the predicted value. And then let me check class the the actual value class is 3.10. So 3.10. Okay. The actual value minus the predicted value class, Control Enter. So you get the residual class, 0.118, 0.18 class. If you check the resid mat class, here, there you go, 0.18 class. Okay, so that's your residual, that's your error term. That's the difference between your actual value and your predicted value. And each of the observations, 526 and all, will have their residuals class. Okay. All right. So going back, so we were able already to compute for the y hat, for the recede mat. Okay. Next class, let me put this in another code. Okay. So far, class, what we have done is to compute for your beta. This is your predicted value. Now, we need to test, class, if your betas, if the parameters, if your predicted values, okay, we need to know if they are statistically significant. So how do we do that? We do that, class, by first, what we need to do is get the standard error. The standard error is just the standard deviation of your betas. It is how far your data, your prediction, your predicted value, your betas deviate from zero. Okay. So we need to get this, we need to compute for this. After computing for the standard error, we should be getting the t-value, the t-stat. How do you compute for the t-stat? We divide your beta by your standard error. Okay. And then why do we need to compute for your t-value? Because we use the t-value in order to compute for the p-value. Okay, so take note of the process here. We compute for betas class. We already did this class. Okay, we already have our beta mat. We have the values here. And then we need to compute for the standard error. Okay, the standard error class, okay, is used in order to compute for the t-value. So how do we compute for that? The beta divided by the standard error will be your t-value, which will then be used in order to determine the p-value. The p-value is used in order to determine if your predictors, your 8 predictors, including the intercept, are statistically significant. Are they statistically different from zero? Okay, which means that they're significant, or are they not statistically different from zero? Which means they're practically equal to zero, which means that they're not significant. Okay, now why is this important? Because your model hinges on this, on your p-values or your t-values. Okay, if this is significant class, which means the p-value is less than 0.05, therefore we can use the value of that particular parameter in our model. We can make use of that. Otherwise, if it's not significant, then that means that particular beta is practically equal to zero. It's not different from zero. So we can choose that in our equation. Okay, so that's the story behind this class. All right, so how do we now? Let's now compute quickly. Let's quickly compute for your, we need first to compute class for the squared standard errors. Okay, standard, sum of the squares of your errors. Sum of the squares of your errors, not squared standard errors, sorry. Sum of the squares of your errors. So how do we do that class? Isn't it we have our recede mat here? These are your residuals class, right? How do we square this? We square this class by getting the transpose. Okay, how do we do that? Let me illustrate. So this is my epsilon matrix class, and it's n by 1. N by 1 class. One way to get the square of this is, okay, is to get the multiply. You can't multiply epsilon n by 1 by epsilon n by 1 class. You can't do this class, n by 1, n by 1. Why? This is non-conformable. So what do? We learned something a while ago. If I get the transpose of this, what happens to this one class? This becomes 1 by n, right? This becomes 1 by n. So it's now conformable. And now you have 1 by 1 answer. The 1 by 1 answer class will be your sum of the squares. of your residuals. So in other words, if I get the transpose of this one, so for example, it's 0.18, the transpose will be 1 by n, right? 1 row by n, and then negative 1.57, and then negative 1.677, etc. Okay? So if I get the cross product of this one class, what I'm doing actually is multiply this one with this one, multiply this one with this one, multiply this one with this one. So I'm multiplying the same elements, 0.18 by 0.18, negative 1.5 by negative 1.57, etc. So it's as if I'm getting the epsilon squared class, right? If we multiply that, and then since we only need a 1 by 1, this is summed up class. We're summing up the epsilon squared. So this value class, epsilon squared sum, is your SSE, sum of the squares of your residuals of your error terms. And how many values is that? 1 class, 1. It's a 1 by 1. Okay? It's the result of multiplying your residual with your exact residual. So that's squaring it, class. And then adding everything. That's getting the sum. The result is a 1 by 1. 1 by 1 can be a 1 by 1 matrix or a 1 by 1 number. So what do we do with that one? Take a look, class, at this. Take a look at our function here. Okay. Remember the cross product, class, of residmat? Ba? Residmat lang to, class, no? Getting the cross product is the same as residmat, comma, residmat. But we need to get the transpose of the first one, and that's what the cross product does. Okay? And then convert it into a numeric. Why is that so? Because we need the number class. We don't need the matrix class. Okay, so let's run this class. Control Enter. And take a look at your SSE, sum of the squares of your errors. It's 4508.07. It's just one number. So how do you get this? You get the difference between your actual value and your predicted value, square it, and then sum that up. That's your sum of the squares of your residuals. Okay. So we also need, class, the degree of freedom. The degree of freedom, class, it will be equal to the number of observations minus the number of predictors. So in others, they call this n minus k minus 1. So n is the number of observations, k is the number of predictors, minus 1 to include your intercept. Okay, so we just use here n minus p, because we let p, class, be the number of predictors, including the intercept. All right, so let's let me remove this. Okay, so let's get this, class, n minus p minus 1. Okay, to get now your, this one is very important, class. This is your variance covariance matrix. Okay, let me annotate this. This is your var covar matrix, class, of your parameters. So it's the same as your sigma squared, the var of your, this is the variance, I mean, no? Sorry, it's the variance of your parameters. Your parameters, class, is your beta, no? Sorry, beta, class. I'm sorry. All right, so how do we do this, class? We divide the SSE by the degree of freedom. Okay. What is your, take note, class, your degree of freedom, class, is this one, 518, class. 526 minus k minus 1 minus, that's minus 8. So that gives you 518. L stands for, it's an integer. All right, so after getting, class, this sigma squared hat, okay, we can now get the variance covariance of your parameters. Its covariance of beta, it's equal to this one class, which is this number multiplied by this one. Okay, X transpose X, remember X transpose X solve class, that's your inverse class. Okay, so it's your sigma squared hat multiplied by your X transpose X. This is the inverse of X transpose. So if you run this class, okay, I'm not going to run it anymore. If you run this, pakirun na lang class yung cov beta, then you'll get this class. Here, cov beta. Here, so what's this? Plenty of numbers here. Okay, take a look at this. It's an 8 by 8 variance. This is called your variance covariance. Why is it called your variance covariance? Because the diagonals class, this one, the diagonals, okay, it's the covariance of the parameter by itself. So this one, for example, the covariance of intercept with intercept, the covariance of education with education. Now, the covariance of a parameter with itself, this one, this is the diagonals class. You can see here that this one is the covariance of female and female. So the covariance class of your particular, let's say beta female, that's equal to the variance class. Variance of your beta female. So the covariance of beta female with beta female is the variance of beta female. Now, why is that important? This one class, the diagonals are your variance class. Variance. So once you have the variance class, okay, if you get the square root of this one, then you get your standard error. Okay. So how do you compute for your standard error? You have to get the variance covariance class, and then get the diagonals class. Okay, get the square root of that to get your standard error. Why do we need the standard error class? Because we will need it for the table beta, standard error, t-value, p-value, right? Beta, you have this. Standard error is this one class. The square root of that, because this is your variance. To get the standard deviation or the standard error class of your parameters, you get the square root of these diagonals. Okay, and then your t-value will be just divide beta by SE. Okay, so notice they're linked. Okay, you'll not be able to get the p-value class without the parameters, of course. You'll not be able to get the t-value if you don't have the standard error. And of course, you can't determine if the betas are significant if you don't have the t-value, because p will be dependent on the t-value. Okay, so let's do that now, class. Let me remove the drawings. Okay, go back here. All right. So we now have our covariance of your beta. So here, class, the standard error of your beta is using the covariance of your beta, class, get the diagonal, and then get the square root. Okay? So the diagonal of your covariance beta, 8 sila class lahat, 8. No? 1, 2, 3, 4, 5, 6, 7, 8. Because you have 8 predictors. Okay, including the intercept. So walo yan, class. So we get these diagonals and then get the square root of that. Here, class. Square root of the diagonals of your covariance beta is equal to your standard error of your beta. And it will give you 7 or 8 numbers, class. Here. So you have the square root the standard error of your intercept, education, etc. Okay? So in the interest of time class, I'll just continue, no? So now, what's the next step, class? The next step is to be able to compute for your t-stats. So how do you compute for your t-stats? It's simply your beta, class, divided by your standard error. Now your beta class is your beta mat is a matrix, class. Your standard error is also a matrix, class. Let's check. Let's check, class. Let's see the class of SE beta. So it's numeric, class. Okay, this is just a vector class. Your beta hat is, your beta mat class is matrix. Okay, so what do we do? How do we compute for the t-stats? We have to convert our beta mat into numeric so that we can divide it by SE beta, which is numeric. So this will now take care, class, of your SE. Again, your beta. You have your beta already, class. 8 all in all, including the intercept. You have now your SE, right? You have our SE values here. And then we compute for the beta divided by SE. This will be your t value. Okay? So this one, as the numeric, we are converting the matrix into a numeric so that we can divide it with a numeric. Okay? So let's run this t-stats. Here, Control Enter. There you go. Take a look at your t-stats. Let's just print this t underscore stats. All right, there. Okay, so we now have our beta, we now have our SE, we now have our t-stats. Okay, so the last one is your p-value, class. So to get your p-value, class, we need your t-stats. So for instance, our let me copy it here, class. Wait, I'll just erase this first. Okay, our t-stats is that for education. Let's compute for education. 11 point. I'll copy this. Control C, Control V. Okay. Now take a look at how we go compute for the p-values. Okay. Pay attention to this one, class. We need PT. PT, class, will give us the probability because that's what we need. The PTs are the probabilities, class. But ang syntax, class, for t-stat is, I'll ask you to please research on this in PT, class. But suffice it to say, class, that we're getting in your basic stat, I hope you remember this, class. This is your t distribution. Okay, sorry for the drawing. This is your t distribution. And then we're looking at t two-tailed, class, because your t can be negative and positive. Okay, so this one and this one. So we're interested in getting the probability of this plus this, class. This plus this. So how do we compute for that? For education, it's 11.03. The positive is 11.03. Okay. We also, of course, we can also get the, okay, 11.03. Since this is symmetrical, this is negative 11.03. The other side, okay. And this one, class, is the probability here and the probability here are the same. So to get the probability, class, of getting a t-value of 11.03, class, okay, we need to add both of this. Okay, so what function do we need? We need to use the PT function, the probability using the t function. Okay, so we need to supply the t-stat, the t-value, and then the degree of freedom. Okay, the degree of freedom. So we already have the degree of freedom, df recede. So we need to post we need to post this one, class. Okay, and we need to get the negative of the absolute value of TS. So the T-stat class is 11.03, okay? So we need to put here negative so that we're referring to this one class. Okay, so if we perform this class, PT of you can use T-stat class, no? Because T-stat is anyway positive, you just get the negative of that. Because this value class will give us the probability from the left. So this is what we need. This is what we will be getting. So we need to give the T value here that's negative to give us, so that it will give us this probability. Okay? And then what we do is just we multiply it by 2, Y class. Because it will give us now this one times plus this one, or times 2. So that's now the probability class of this 11.034 stat. Okay? And also for the others class. Kasi yung T-stats natin, di ba, there are 8 all in all. So I have just a few more seconds. Okay? So let me remove this. Okay. So how do we get the p-value class? Okay, we run this. Oops. Okay. We get this class. This will give us the probability from the left side. Okay, kasi ang default class ng, if you check this function class, lower tail to from the left side. And then we just have to multiply it by 2 so that we get also the right side. Kasi ang kinukuha natin probability, kasi class yung t-stat natin, two-tailed. So which means that we have to get both sides, the left hand, the left lower left and the upper left. So that's why we're multiplying it by 2. So if we get this class, control enter, and then print the p-values. There we go, class. Okay. So take a look at education. The p-value is, okay, that's very, very low. So how do you get this? 1.4, move 25 places to the left. That's negative 0.00000, etc. So that's a very, very low p-value, and it's lower than 0.05, which means that education is significant. Okay? Si non-white, hindi. Kasi the p-value is to the negative 1 lang to, move one place to the left, that's 0.79. No? So that means the p-value of non-white is very much higher than 0.05. Therefore, the p-value of non-white is is not significant. The parameter non-white is not significant. Okay? All right. I have to end here. Ito lang class, no? Let's just run this class. Let's run this code here. Okay, i-run natin to class ito. Okay? So LM class, this is the LM function where you are wage, regressed on education, experience, tenure, number of dependents, etc. And then we get the summary. So let's run this. Paki-run to class na ito. Plus the summary. Control enter. And then you see the result here. Take a look at this class. This is what we want to do, no? Using the matrix. This is the estimate. Meron na tayo nito. Standard error meron na. T-value meron na rin, class. Itong p-value class ito. Tingnan nyo class yung yung sa intercept. 0.0117. Tingnan nga natin kung pareho yung p-value. Here. Intercept class. 2 decimal places. 1, 2. So that's 0.0117, right? And it's exactly the same as this one. P-value. Here, ano to? Sana si, yan, 0.0117. Okay? All right. So next meeting class, we finish this. Tapusin natin itong, itong using the functions, using the matrix, and then we compare it with the LM function. Okay? Then after that, we now go to a problem, no? We're not going to use anymore the matrix. Kasi ang objective natin dito, class, for us to be able to see what's happening behind. How was this generated, itong ano na to? Di ba na-generate na natin si estimate? Ito X transpose X, inverse X transpose Y. Itong standard error, saan natin nakuha to? Kinuha natin yung covariance ng beta natin. Then we got the diagonals and then got the square root. Ito yun. T-value, paano natin nakuha yun? Plus T-value, just divide estimate by the standard error. Okay, and then yung p-value, ito na yung PT function natin. So all of this, class, we were able to produce using yung ano natin, lahat ng mga functions. Okay? But in one function, LM lang, class, lahat na generate na. Okay? But we're confident that we were able to generate this also. Okay? All right. With that, class, thank you so much. I'll stop recording. I'm going to see you in class